Good morning. Welcome to episode number 38 of the ZOOMTOWN experiment. Today's video we're going to go over a lot of the changes I've done with line following. And that's the implementation of a number of features. Primarily, we were adding 1-inch markers all along the straight lines, and that was to allow us to get greater precision with localization and combining that with the encoder feedback so that the Zoomie would know where it was relative to any given road section. That also required the implementation of a whole different methodology of how I'm handling some of these motions, and I'll touch on that a little bit today. But we also needed to have a way of recognizing from where one line or one motion segment ends to where the next one starts. We have to inform the system that that is the 0 point, and it's a very specific point. Furthermore, while that seems good, at the start of every line I would need to tell the Zoomie you are at 0 at this exact point. In truth, every trip that the Zoomie makes starts and ends in a driveway, and therefore the Zoomie would always enter a roadway from a driveway somewhere in the midpoint of that straight road section. Then it would be all over the place until it gets to the destination, which the last road segment would be a straight road, and we would exit that road in the middle somewhere to pull into a driveway. So I needed a way when the Zoomie backs out of the driveway to be able to say, okay, when you back out, when you encounter this, you will be exactly at 7 inches or 12 inches, whatever the case may be. Now, for you folks that are in the rest of the world outside the United States, I will be using inch markers and that phrase a lot. Anytime you hear me say 1 inch, just substitute with 25 millimeters, and you'll be right on path with what I'm talking about and a good scale. Now, the first thing I want to start with is a demonstration of the line following as we've been using it. Now, that particular routine has been slightly changed over the course of the last few months, and some of it intentional, some of it unintentional. It just needed to be changed. Now, early on, my line following routine, I kept it very minimalistic because I didn't want to waste a lot of energy and time on that, cycle time. So I never really tested to see its robustness, meaning if something kind of changed the direction of the Zoomie a little bit, if it would recover. The very first few times we talked about line following and I was demonstrating, and it didn't do curves. I never had an intention to do curves. So it never really was tuned to perform well on turns because the plan was to use encoders. Well, that plan went out the window and everything changed. But let's start with the foundation of what we're going to talk about, line following. So I'm going to go ahead and run that over here on the test track. Okay, made that turn perfectly fine. Came to a nice smooth stop. I'll do the same over here. You'll notice that I'm just kind of plopping the Zoomie on there, not being super careful. In fact, we'll start it out looking like that. That's kind of a bad start. Picks up the direction beautifully. We'll come back. Now this is where it gets a little more interesting. I would say that's a pretty robust system for line following. I'm pretty happy with how well that recovers and behaves. Now that's just using a proportional control, not the integral or derivative of a full PID system. Generally, in this type of activity, the Zoomie would, or the device that you're controlling with PID, if you were to knock it off like I am, it'd just sit there and wiggle around for a while and finally settle in. There could be all kinds of nasty hyper behaviors. In this case, with just proportional control, I am thoroughly and very pleased with how it's behaving. So from that, I could use this as a foundation to do all the other changes that I needed to do for positioning and localization. So now we'll go back to the test track, and I'll show you the layout and how that's all changed substantially. The nice part about Test Track Z, literally I can kind of pick it up and move it around without too much concern. Get the Zoomie out of the way. I'll try to get this position good on the camera, and I apologize. A few episodes back I had all kinds of trouble filming over here, trying to get the camera positioned, and I think we should be okay for what I'm going to be demonstrating. Okay, one of the things that'll come up soon will be our parking spaces. This is where the Zoomie would be parking in a driveway. Here's the road that would be in this way. Remember, I'm here in the United States. We drive on the right side of the road, not the left side of the road. I apologize to those of you in other parts of the country or the world where you do it the other way. But what we've got from here, this marker on this edge, now we're traveling, let me get the Zoomie there so you get an idea. And okay, we're traveling this direction. On the camera, it's to the right. The black tape is actually on the curved part of the line, right at the start. This edge of it is right at the start of our straight line, going all the way this way. What I need to do is sense the transition from black tape to no black tape. That is a very important aspect of what we're doing here. The tape gives me a pretty quick transition point between on tape and off tape, especially when I went to the black color. I believe we talked about that in episode number 36. So that gives me a very precise location, probably within about a 1/2 millimeter or about 20 thousandths of an inch. That continues all the way across here. So every 1 inch, 25 millimeters, I will see that point, that very precise point with the TCR T5000 sensors. So that's great. Now, because I can see those and it's a very precise, consistent reading, I can use that point in time and travel to update where the Zoomie thinks it is, update its position, and say, you are here, with great accuracy. Now, the other thing that has to happen along here, and I'm going to grab another Zoomie just to help with some explanation. I'll put the body of that one, number 5, right in the parking spot here. Now, as we're going around this curve, I need to establish a reference point so that from once I enter this line, I have a known reference point, a datum, an origin, a 0 point, whatever you want to call it. And the way I do that, as I come across this line, and when I transition from the marker to the line following guideline, if I see a magnet with the left Hall effect sensor, I am going to say at this exact position, will be the 0 point or datum for this entire line. Simple enough. So now I can get a datum. This is 0, this is 1, this is 2, this is 3, this is 4, 5, and so forth. Makes for the math to be very simple with creating absolute positions along the travel here. Now comes the next part that's a little more difficult. All trips for the Zoomie start in a driveway and end in a driveway. So when the whole system starts up, everybody starts in a driveway. They're not going to cross this datum point. So let's simulate that. We'll back out of the driveway. We will pivot turn and be in about, I think it'll be a little closer. It'll be right about here. And right here and right here are two magnets. Now there will be a driveway here, and I don't know, yeah, you can kind of see it on the camera. I'm preparing to put another driveway here. So I've backed out and I'm on the roadway, and I know I'm heading in that direction. What I can add to this instruction of the next move is this. Go in that direction and go to a position, but when you encounter a black piece of tape, that transition, and you see a magnet with the right Hall effect sensor, I'm telling you that that point will be X number of inches. It will be a specific point. Now back here, this specific point is always 0. But at this point, we are 5, 10, 15, so that'd be position or inch number 19. So from here to here is 19 inches. So if I told the Zoomie, as it moves forward, it encounters that magnet and a black stripe, you are now at position 19. And likewise, when I back out of this driveway and then I encounter this one, this magnet, which you can't see because of the camera angle, that magnet in this stripe is position number 24. Pretty simple all in theory. The first problem I ran into, I was using about a 4 millimeter diameter magnet, about the size of this yellow dot right here. The problem is the Hall effect sensor in how it sees this versus the photoreflective sensors, they don't cover the same area as they're sensing. So I couldn't get this to be turned on at exactly the same time that the photosensors see the trailing edge of the black tape. So after I tried and tried and tried, I thought, well, the hell with it, I'll just buy a bigger magnet and put them in the board. And that's what I've done here. These magnets are right around 13, no, a little bit bigger than that. I think 15 millimeters, which would put them at about 13 millimeters, right around a ½ inch in diameter. So now this area, the Hall effect sensor stays on for most of this distance, and then I can monitor when the black tape transitions back to line following, and I can trigger on exactly that spot in space. Not so bad. The next thing that changed on this happened to be how I wanted it to work once I started getting into it. I had no plan to do this, but there was an advantage. Now, all along, most likely all my movements, I don't like dragging him around, I would say I'm at this point for whatever I'm starting here, I would tell the Zoomie to move 3 inches. So 1, 2, 3. And if I wanted to move another 3 inches to the next driveway, it'd be 1, 2, 3. And I would tell it 3 inches. This system allows me to use absolute coordinates as opposed to incremental coordinates. What do I mean? Okay, I start here. that is 0. And if I told it to go 3 inches, 1, 2, 3, it would go here and stop. Again, in incremental coordinates, if I say go 3 inches, 1, 2, 3, and stop. At this point, that is 6 inches away from this line. Okay? The new system, I don't tell it how far to move, I tell it what position to move to. So now, from here, I'm using absolute coordinates, this being the reference point of 0. So, from 0, go to position 6 or 7. Boom, goes there. Now, if I tell it to go to position 6, it's already there, it won't move. If I need to go further this way, the number counts up, and if I said now go to position number 19, it goes to there. So we're telling it what position to move to, not how far to move. So that's the difference between absolute and incremental coordinates. Incremental, you tell it how far to move in this increment. Absolute, you tell it what position to move to. Very different than what I had originally planned, but I'm seeing advantages to using this methodology. I was somewhat forced into it as well because of this needing a reference point when I back out of a driveway. And some of that will make a little more sense in code when we take a look at that. But this is now what our road surface will look like. Perhaps not without the potholes that are here where I had big magnets in there before, but I'll have our traditional guideline, black tape as our cross marks, spaced apart 1 inch or 25 millimeters all along there. And then I'll have a large 13 millimeter half-inch diameter magnets in very specific locations to specify whether this is the origin or datum point for a line, or this is your reference point. Once you see this, I'll tell you when you encounter that, you will be at this position. And same with this. The yellow dots here are serving no purpose other than for me to count real quickly and verify that the Zoomie, as it's going along, if I told it to go to 7 inches, it would be here. So that would be one dot plus 2 more black lines. Just a quick way to keep track of everything. Now, conceptually, this can be somewhat confusing if you're not used to working with incremental and absolute coordinates. And of course, for you folks in the metric system, I'm using inches, and that doesn't help with clarity and understanding. I'm just one of the fortunate few in this crazy country where I can play in both metric and inch. I don't really care one way or the other. They're both systems that are useful, and they're just specifying some distance relative to our discussion. But the program that I'm going to show you, I got some more cleanup to do in it before I really want to put it up on the web, and hopefully by the time this gets published in probably 2 weeks from right now, I'll have those cleanups done, so I'll post this version online. Now, this is a very stripped down version. I've really gone backwards from where we were before the big meltdown with everything is wrong. So I'll have to add that other functionality back in, and if it changes how I implement the other functionality, I'll explain it. If not, I'll just drop it back in the code and we'll move on. And again, most of this focus that I'm dealing with right now is all to do with the line following motion type. The naming now, I'm kind of going into Zoomie 30, kind of a version update, and I'm using that in the file naming as well. I'm currently on Z-30-07, and that'll continue to count up. From your perspective, it looks very random. From my perspective, it's immensely important to try to keep track of all of this stuff. I've got a bunch of notes in here. But we're going to go through the whole program, and I'll go into detail where I think it's important. Otherwise, I'm just glossing over it and speaking more conceptually. Just as before, load our libraries, configure our hardware, our I2C interface, our encoders, all that's the same as it was before. Global variables, this is changing dramatically, not necessarily with not using them or using them, but changing the names of a lot of them to be more representative of what the variable means relative to this new version. So I do apologize for that, but in order for me to keep track of it in my tiny little brain here, it helps when I change variables so that my mind recognizes I'm in a different system than I was a week or 2 weeks ago. So I do apologize for that. But this is the area code I really got to clean up. Status light control. I was using the status lights to see when, to mirror what was going on with the TCR T5000 photoreflectives. Anytime they would see the line, I would turn on the red LED. When it's not seeing the line, turn it off, and that was helping with debugging. Position handler. This function or functional group of the program had to do with dealing with the encoders and extracting useful information out of them. We already discussed this, and there really wasn't a lot of change in this. I did switch, and I believe I discussed all this, the way I'm working with the encoder data. In the past, I was always taking these absolute rotary encoders and taking that data and splitting it out into not what rotational position it's at, but rather how far it moves since the last time we looked at it. In the old system, that made better sense, but it created problems as well. So now I'm actually working directly from the encoder value and then counting the revolutions and developing a distance traveled. So the code here, I believe we've already covered. It's very well documented, so you should be okay with that. Now we're going to start talking about the critical part of the code. We're going to start direction and the motor speed control. This was exactly the same before. If the wheel's got to go forward, we tell it to go forward or reverse, and that sets the outputs. There's two adjust velocity routines, and this is likely going to change, so I won't go into any detail, but adjust run velocity is being passed in a value between 0 and 1 now, and that represents kind of a percentage of our duty cycle, meaning 0 would be 0 duty cycle, 1.0 would be 65,500 for the duty cycle value. And then I've got another one here where I pass in exactly the duty cycle. And I'm using this one to make sure the motor is turned off when I don't want, or the motors are turned off when I don't want them running. And I believe this code was very similar to what we've already had. Now the motion control. And this is where it's, a lot has changed. And I'm going to branch off, talk in a conceptual idea before we go into the code. In the past, I would create the motion and start it, and then not with anything specific to line following or turning or anything like that. The other portions of the program would manage all the different things that needed to happen during that motion: acceleration, deceleration, keeping track of position, and all that. One of the things I kind of discovered is that instead of doing it that way, keeping these things very separate, now when we're performing line following, I'm constantly calling a function that handles the line following motion. And so it handles acceleration, deceleration, position tracking, in our case, in this example, keeping track of where the markers are, our zero set, or our midline travel, position resets, all of that stuff. So This structurally is very, very different. It wasn't intentional. It kind of happened naturally, if you will, as I'm working on developing this whole new way of tracking position. Will it work in the bigger picture when I add other motions? I don't know. I'm not that far along yet, but we're going to find out real soon. This whole code here right now, I call it start motion control. This is a code block of several functions. And then finally line follow, steer velocity correction. So, and that's the guy that's doing all the work. And then I just started adding in pivot turn so that I could start experimenting with multiple consecutive motions. Okay, so let's go through these kind of quick. Most of them are real basic. We're getting the Hall effects sensor states. We've got two Hall effect sensors, a right one and a left one. And I'm writing that value to a variable called pset underscore state, whether it's on or off. And then zset state, on or off. And then I return that to the caller. I get my marker state, which means that's the TCRT 5000 looking at the black tape passing underneath it. And what I'm looking for there is a transition state. That's the most important part to what we're doing. I don't want to know the whole length of the tape or any of that. The only point in time that's important to what we're doing is that transition from being on the tape to passing beyond it, or if you understand rising and falling of digital inputs. Rising is it goes high, falling it goes low, and that's exactly what I'm doing with get that marker state. I want to know, is it rising? Well, I don't care about that. I want to know when it falls, because that gives me a very tiny point along that travel that I can relate to or record that position. And we do that here. We were passed in the readings from the sensor, the TCRT 5000, and if that's less than the black marker threshold, meaning lower value than what we're seeing from guideline following, for both the left and the right one, it means I'm on the black tape. If it's if the marker state, or if the readings from the TCRT 5000 are not lower than that threshold, that means we're on the guideline, so my marker state is I'm off of it. So on meaning that drop or on the tape, and then off meaning it's back to guideline following. Now, all we need to do to find that transitional point then is record what the state was on the last read and compare it to the new read. So if the past reading was off and the new reading is on, we've transitioned onto the black tape. Now, if the past reading was on and the new reading is off, we're transitioning off of it. So that's my falling edge, and I'm just abbreviating that as simply T off, transition off. And then I take the state, put it into the global variable so it's preserved after I exit the function, and then I can keep making that comparison essentially every 6 milliseconds. This particular routine is simply looking at the error of where the TCRT 5000 is relative to our guidelines. Am I to the left or am I to the right, and how much? And that data is passed into this function. So what it'll do is, based on that error and the amount of adjustment that's calculated to get it corrected, we will take that, and that actually comes output from the PID calculation a little further down here in the code. So we take that error and that adjustment amount, and we apply that to our target value, our our current run value for velocity. And that's based on our target value. We're always specifying a target value to achieve, and we're either going to add or subtract the adjustment to speed up a wheel or slow it down to cause it to steer and stay on course. Once that calculation is done to get these L% runs, it gets passed into adjust run velocity, where we're passing in that 0 to 1 range. And then from there, that'll convert it into duty cycle for the motors. There was something else in here I wanted to talk. Oh, you'll see me using the percent, target percent run, and that change of 0 to 1 in specifying velocity. Remember before I was saying I change variable names so that they're appropriate to what other changes happened? This was helping me keep track of it. I could have used the old numbering system, but it required yet another translation between the desired velocity and the duty cycles. So by changing the name, I can quickly recognize I changed that substantially. Now we're going to check and handle for decel. The deceleration routine I wrote before is very good and functional in other systems, but it was problematic in our situation here. I didn't want to really dive in and make it, improve it, make it better, because it was getting way too complicated, and I didn't need all that complexity. So this one, when I call this function, it will be passed in motion status, or I'm sorry, not passed in. We will record the motion status, whether we're stop, braking, or we're moving. Okay, either we're moving along, cruising at highway speeds, or we're slowing down because we need to slow down to the end of the road, or we're completely stopped. That's the purpose of this routine, is to update that, and then update based on where it is relative to distance to go. In fact, this is still in incremental units, and I will be changing that to absolute units here shortly. But the logic is very basic and simple. If we're really close to the end of the line, less than 50 thousandths or 1.25 millimeters, I want the thing to stop. And I'll reduce that number later to an even smaller amount. If the distance to go is less than a half an inch, or about 13 millimeters, I want to slow down to the speed of 30%. If it's less than 1 inch or 25 millimeters, slow down to the speed of 45%. And if it's an inch and a half away, 25 plus 50, 13, 38 millimeters from the end, we'll slow down to 60%. And otherwise, we're just moving along at cruise speed. Now, this motion status is used down in the main loop to know whether we're ending the move, we're cruising along, or if we're braking. The biggest thing is the end of the move, because that is a trigger to go on to the next particular motion segment, be it another straight line or a turn or a pivot turn or whatever we're doing next. I've got a couple of global variables being defined here. These will go back up into the other area where I define all global variables. I've got a lot of global variables in here. Most of these probably aren't needed anymore. So that's, again, part of that cleanup. Hopefully you won't see it when I post this up on the website. The other thing, the name kept changing over a lot of experimenting here, but I'm calling this line follow steer velocity correction. We're line following, and I've got a steer in that methodology, and I'm doing that with velocity corrections because I don't actually steer with a turning wheel. Just only way I could keep it straight in my head as I'm going through this and developing it. At this point, I want to remind you that this function is called every 6 milliseconds. So we don't call this function to start the motion. we call this function to maintain the motion. Hopefully that makes sense, because in the past we started the motion and now we're using it to maintain, and the logic is quite a bit different, and the program flow is very different as well. But we've already covered briefly what get Hall states is, and we're going to put those values in P set and Z set. P set references where we are over here. These would be position sets, as I'm calling it, or P sets. When we back out and midway through the line, I need to tell it what position it's at. Over here at the start of the line, this would be Z set. We're telling it this is the 0 point. And so those states, when the sensor sees that, are in here. LLS and RLS is just the sensor readings from our TCRT 5000 photoreflectives. On center is a constant I've been using, and that is essentially what both of these sensors would be reading if the Zoomie is on the center. So that's kind of like the baseline number. Here is the left error amount, right error amount, and those are basically taking that minus the reading, and now I've got an error amount. Now I want to combine both of those into one, so I take the left arrow minus the right arrow, divide it by 10,000, and then that'll scale the error amount down into a useful value. Kind of this is part of the proportional aspect of this, if you can kind of just accept it as that. Next is my KP, which would be the proportional factor or a proportional adjustment that I'm making to this data. In a full PID routine, you'd see K, the typical wording is KP, KI, I for integral, KD for derivative. I don't want to add the I into D because it's behaving really good right now. But then we calculate the amount of velocity adjustment I want by taking our error times our proportional. And then I perform the steering adjustment, passing in the error and the adjustment. The marker state, now I want to look at the black tape at this point. Am I on it? Did I transition off of it? Where am I? And that's what this function is. We pass in LLS and RLS, which were the readings from the TCRT 5000s, left and right. Now this section of code here is where we'll probably spend the bulk of this discussion. This video is getting very long. I apologize, but I hope you want to understand all this. We're going to be making decisions in here based on whether or not the Zoomie is on top of a magnet of one of two types. The position set state is looking for magnets on the right Hall effect sensor. Over here on the the test track, this is a position set magnet, and so is this one. So at this point or this point, I am going to say you are at this inch position. In this case, it's 5, 10, 15, 20, position 19 inches. That one is position 24 inches. These dots are representing increments of 5. So that's what we're seeing there, but there's two conditions in order to do that. I have to see this magnet on while I transition from seeing the tape to seeing the guideline, and that's marker state transition off. Now, if I want to perform that action, and that's what this is. This variable would be set when the motion is created earlier on in the process. And now we're going to set our inch marker to the value being that we want it to be at. So if I want it to be at 24 inches, I would pass in 24 inches at that, set our absolute marker counter to that. Next off, we're going to record this position, this marker position, which this is incremental, and that's used to calculate future positions as an offset. That'll kind of make sense in a little bit here. That's these two guys. Next up, we're going to reset this these two variables, reset the counter amount that we're telling it to change to 0, and turning off the feature. We don't want it to be performed if it sees another magnet. Now, if that wasn't on, in other words, in this particular case, we're just passing over that exact condition, all I really want to do is increment my absolute marker counter, position counter, by 1. I'm incrementing it by 1 inch. So as we move along, this counter, I'm adding 1 inch every time. That makes it a very simple translation between what we're seeing there and to the mathematical calculation for where it is along the trip. Now at this point, all we're really dealing with is just 1 inch increments. We'll get into the between area in a moment. So this math should be pretty straightforward. Now, in the 0 set state, which would be the magnet all the way back here at the start of the line, if that's on and we just transitioned off the black tape onto the guideline markings, we're going to record this position, incremental position, into this variable for further calculations. We're going to establish this position as 0. That is the 0 set function. We're saying you're at 0. So currently the left inch position absolute is 0, right inch position absolute is 0. And our absolute marker counter is 0, because that's 0. Every time we go up 1, that absolute marker counter increments by 1, and that's how I know which inch I'm at. Finally, if I experience a marker and no magnet, either P set or Z set, then I'm just transitioning from the tape onto the guideline marker at that point. So at that point, again, I want to increment my absolute position marker and then record this incremental position into the absolute marker position. Again, at this point, all this stuff here is dealing with 1 inch increments all the way along, and whether we're at a condition of left magnet line, right magnet line, or just line. And that handles a lot of all the work we got to do for absolute position tracking. And by the way, at every one of those points, we're within, if I just say you're at inch 13, I'm realistically at inch 13 plus or minus a half a millimeter. And that would vary depending on how fast the Zoomie's going. And I haven't gone into that much depth yet on working those details out to see what my resolution would be, because we're always dealing with time and motion, and these things stretch out and shrink up. So that gets a little, we'll call it a lot confusing as we work through that. Now this here is takes kind of everything into account and creates an absolute position based on everything we just did in those 3 lines. So these two, the left inch position absolute equals the left inch position incremental minus our marker point. Remember these? So now I'm subtracting that marker point, and that just gives me essentially the distance traveled within or between 2 marker lines. And from that, I'll add my marker count, which is a count for every inch I've traveled. So this, if it's 7 or 10 or 13 or 40 or 96, that means 6, 7, whatever number of inches. This little calculation here is just telling me difference in the encoder count or distance traveled from the encoder count only in that little 1 inch travel distance. That gives me a much greater precision. Now, if there's a lot of steering on there, like before when I was poking the car and it would go way off course, this could still have a substantial error in it if we're measuring right at the point where the Zoomie is really twisting and fishtailing around. So this still isn't perfect, but it is a huge improvement. And then finally, the next thing that we're doing is getting our left inch distance to go, and that is calculated by the distance that we need to travel, which is our position that we're feeding to, and our absolute position, where we are. So left inch position absolute, which is this guy, and then this is the distance or position I want to travel to, the balance being our distance to go for the move. A lot going on there. And then finally at this point I would check and handle the computations for deceleration. Am I getting close to the end? Because now I know the distance to go, and if so, adjust the velocity. Wow, right? There's a lot going on in there, and I still think there's some refinement in it, and I really won't know that until I get into a much more in-depth testing situation, which will be happening on my next available workday here in the lab, where I've got to run a bunch of tests, and then I can see behavior and adjust, and as I come in and out of the code, because that could be 2 weeks from now, might have to rechange some of these variable names so that they make sense to our current version. So now with that, I'll demonstrate a few applications with it, and then we'll call it an end for this video, because I'm sure you're all just sitting there yawning by now. For our testing purposes, I'm down here lower in the code, and I'm inputting into the trip plan. We're actually running the trip plan. And for our experimenting here, I'm just working with forward line sensing, forward line following sensor, and I'm saying move 20 inches. And we'll be tinkering that up and down. So if I say I want to change it to 7 inches, this is where I'm doing it in code. I will also have to manually do this for right now because it isn't part of the system. And you'll see that here. Remember earlier I was talking about force absolute marker status and marker counter. Here I'm saying I want to perform it, and when you get to that position with the right magnet and exiting a line, set that point to 7 inches. I've got to comment it out because right now I want to ignore that operation and do nothing with it. But this is when the whole system starts running. If I'm telling it to make a forward line following steering movement, this is all the variables that would get set to cause that motion to occur. So I'll be changing some of these. I'll show you as needed when we're doing this. So let's go ahead. Going to get that up there so I can kind of clear that. Yeah. Now at this point I told it to go do not do mid-travel updating and to move, make sure I'm doing this right, 20 inches. So 20 inches, 5, 10, 15, 20. It should stop here. Now the other thing you'll notice, right now I'm just worried about where the sensors are. The sensors will stop at 20 inches, which this is my penciled in mark that kind of goes along where the sensors are. So the front of the Zoomie, because it's rounded, will actually go past that point. I will be able to see that mark there, and it should be very close to where we want it to be. And the other thing you'll notice, I thought I knocked the tire off. I'm just going to kind of drop this back here at some random distance between here and here. So that's kind of what we're doing here, is allowing the system, regardless of where he starts, if we're within reason, it will zero itself here and then move to the position of 20 inches. So let's see what happens. And believe it or not, he's stuck. The Zoomie on this slippery surface can't pull this cord along with it. Oh, that's been a problem. Usually I've got this cord up here on a wire suspended above. In fact, I'm just going to try and do that right now. Hopefully it won't keep knocking into the camera. We'll try that. Worst case scenario, I'll have to move it again. So let's try that again. We'll clear and we'll run. And I'll move my finger out of the way. That's where the front of the Zoomie stopped. That's 20 inches, so back where the sensor is, it was right in this area. Try that one more time. Actually, let's just give it a different value. I'm going to say go to 30 inches, way up there. And it stopped exactly. Ooh, you can't see that. I'll bring it back a little bit. And again, with the camera angles, unfortunately, you really can't see. So I apologize for that, but can only do so much with cameras. I'll hold my finger at the point, and at the front of the Zoomie stopped right there. Now, let's take this as an example. Now, if I were to start it here, for example, without passing over the zero reference, it theoretically would be lost during this motion. So this isn't a full, true, absolute encoding system. I still need to have some index mark from which we can position. And that was what led to this next thing I'm going to show you. Now, as mentioned, the Zoomie will back out of a driveway and end up somewhere about like that, somewhere between here and this line, this being the center line to get into the driveway. So in code, I'm going to say I want it to move to 25. That's where I want to end up at. And this is actually position 9. So how do we do that? Well, we would know that at the start of the move, because we would have had to have put the Zoomie in that location. So I'm saying this one was what again? This is 19, and I want to go to 25. 1925. So I am going to set that point. When it encounters this, you're at 19 inches. And we're going to perform it. And I can't remember because I was jibber-jabbering. Right there's where I would put 25. So now if everything works right, as it's going forward, it sees this point. Once it gets to here, it'll say, perform the position update to what we told you this is, 19 inches, and continue on until you get to 25 inches, which would be hopefully that if I counted my dots right. How sweet is that? And that, just so you're aware, let me kind of move this guy around a little bit. We'll run it again from there. And again, it stopped in the right spot. And I'll bring it all the way back to here. How cool is that? This system, while not perfect, is a huge leap forward from where we were a couple of weeks ago. I still think there is potential here for problems, but I've taken the positional error, exaggerated, from this much down to that much. I'm still not in my millimeter accuracy, I don't think, but I've gotten very, very close with it. So I'm going to have to continue down this path for a while, and I won't know how bad it is until we get further with our experimenting, which is why it's called the ZOOMTOWN experiment. Everything's try this, experiment with it, and see what happens. So right now, things are looking really good. My next steps are to start combining some movements, because I think the line following and moving along straight lines, and even around our sweeping curves. These are all sweep curves. Those two are essentially just going to be line following motions. I don't have to do anything along them or stop on them or know my position. I just need to transition through that curve. When we get into the big layout, we're making tight turns in the city area. We'll be making pivot moves, or pivot turns. One wheel will stop, the other wheel will drag the Zoomie around and get it headed, hopefully, in the right direction. And I just started on that this morning. So now I'm going to start building up combined motions to hopefully get a full trip working within hopefully the next few episodes. That's a lofty dream, but that's what we're shooting for. So I think this video's run plenty long enough. We'll wrap it up here, and I look forward to seeing you in the next episode. Thanks again for watching.